Okay, as we continue through quantitative methods basic concepts, our next reading here has to do with discounted cash flow applications. Kind of builds on what we've already covered. So let's jump into that, see what they've got for us here. We've got a concept here called net present value, and we use this with projects. Give you a little context here. Say we've got a project where we've got to invest $1 million today, and we've done some projections of how much we're going to earn on this project, this piece of equipment, whatever, over future periods. Well, now we've got to look at the present values of those future cash flows and compare them to the cost in today's dollars, the present value. So that CF0 here, that's usually a negative number. And right here, this is usually the initial outlay. And then this piece over here is the present value of all the future cash flows we expect to get. So this idea of net present value is what's the present value of those future cash flows net of the cost of getting them, the investment that we must make. And we can calculate this using our financial calculator. So here's an example of a simple net present value calculation for a simple project. We need to invest $100 today, and we expect to get cash flows of $25, $50, and $75 at the end of each of the next 3 years. So the net present value is the present value of these minus our initial cash flow. So we just discount at 9% each of those future cash flows, get their discounted value here, or the present value of each of those cash flows, their value equivalent in time zero, today's dollars, add them all up, and we get a net present value of $22.93. Now that's positive, so what it tells us is that this project is something we should do. The present value of the future cash flows is greater than the initial outlay. And we can think of net present value as the change in wealth, or at least the expected change in wealth in today's dollars, present value terms, from investing in this project. So our decision rule with net present value is if the net present value is positive, that's expected to increase wealth or increase the value of the firm, and so we should accept that project and do it. Now, a related concept is the internal rate of return. And you can see from the definition that we have there that this IRR is the discount rate that equates the present value of a series of cash flows to their cost. So you can see I've set up the net present value equation here, and the IRR is the discount rate that's going to make that net present value zero. And if you think about it, that also means that the present value of the cash flows with this discount rate, this IRR, is just equal to that initial outlay. That expense at time zero. And we can solve for that on the calculator. Now, we know we had a positive net present value. at a discount rate of 9%. So the discount rate that's going to make that equal to 0 needs to be higher than 9%, right? We use a higher discount rate. That's going to reduce the present value of those future cash flows, and we can get that just equal to the initial outlay. So if we use the calculator and solve for this internal rate of return, we find out that it's 19.44%. And so what we've done on this slide is discounted these future cash flows at 19.44%, taken their present values, and when we add those up, they just equal the initial outlay of 100. So now, at a discount rate of 19.44%, the net present value is 0. So that's a related concept here. And we can do compute IRR with the cash flow function. Now we're not going to run through all the calculator strokes here. They're explained well in the Swayzer notes. We've got a number of examples in there how to do it. And we also use this concept in corporate finance, and you'll learn more about it there. But we wanted to introduce them here in this reading on discounted cash flow applications. Now there's some possible problems with IRR. We've had simple projects where we've had one negative value, the initial outlay, and then we've had a series of positive values. So if there is an IRR, that is, if there is an interest rate that makes the net present value 0, that's a single make more of an investment at some point in time, or maybe we're planting trees and we need to spend money thinning those trees one year or whatever it is. If we go from negative to positive and then back to negative at some point, then there can be more than one IRR. There's more than one interest rate that'll give a net present value equal to 0. And mathematically, they're all equivalent. We can't differentiate between them or among them and say, yeah, this is the one that's right. So that's one of the problems with IRRs. With more complex projects, we can get multiple IRRs and can't make a decision based on that. The other issue with IRR is with a series of cash flows, we could rank them by their net present value. Remember, net present value was a measure of the expected increase in wealth from doing this project. And so we can rank those and say, well, if I have to choose among 3 projects, I'm going to choose among those with positive net present values, choose the one with the greater net present value. Now we can also rank these projects based on the IRR, but the rankings could be different. One project could have the highest internal rate of return, but a different project may have the highest net present value. And net present value in that circumstance is the one we want to use. Actually, from a theoretical basis, the net present value is always the best choice. And as I mentioned, you'll get more on this and more applications of it in net present value. Excuse me, in corporate finance. Sorry. Okay, next concept for us here is a holding period return. Very simple concept. It's just the percentage increase in wealth or percentage increase in a number over a single period, and that period can be of any length. We can talk about a holding period of 2 days or 3 years or 1 year or 9 months or whatever. So a holding period, unlike our stated annual rate and our annual compound rates and all that, are for various periods. So for an example, look at an investment purchased 9 months ago for $9, and it's now valued at $10.20, an increase of $1.20. So what's the holding period return? Well, take that ending value of $10.20 over the beginning value, subtract 1, and we find that that increase has been 13.33%. So we'll say, well, the 9-month holding period return for this is, or was, 13.33%. As another example, a stock purchase a year ago for $29 just paid a dividend of $1.30 at the end of the year, and after paying that dividend, its value is $30.50. So what's our holding period return? Well, here we've got a total return because we're including a cash flow. So we've got a cash flow and the ending value. So we're just going to use the total ending value. We're going to add those two up. So now our numerator is the ending value of the investment after 1 year. The beginning value is 29. Take ending over beginning minus 1 and say we have a 1-year holding period return of 9.66%. Our next two concepts we need to deal with are time-weighted and money-weighted returns. And this has to do with a portfolio. And we really relate it to performance of an account manager. Now, typically, say in a retirement account, if I'm the equities manager, I have control over what equities, what securities I select for the account. But I don't have control over funds coming into the account or funds going out of the account. That's going to depend on the retirement plan, how much contributions, how much payments are being made out of it, and what the timing is. So in this case, we look at the time-weighted returns. This takes out any effect of cash flows in and out of the account, because if they're not choices made by the investment manager, then we shouldn't include those in developing a way to evaluate manager performance. So the periods can be any length here, because if we have money coming into the account on this date, well, we want to measure over this time period when no significant funds were in or out of the account. And those periods can be any length, and we're going to string them together here by multiplying them for the whole period. So ending value over beginning value, we know that's 1 plus the holding period return for these various holding periods. We multiply all those together, and then you see we've got an exponent here, 1 over the number of years, because we're after an annual time-weighted return. So if our data period is a year and a half, then we've got to take that to the 1 over 1.5 power to get the annual equivalent return. So the periods can be any length. We calculate it for this full period, and then if that full period is a year, we don't have to do anything. If that full period is less than or greater than a year, then we have to adjust that to get an annual time-weighted return. And again, these periods are periods between significant cash flows, either into the account or out of the account. Now, money-weighted returns, on the other hand, take account of those cash flows in and out of the account. And I guess if a manager market timing, in that he was deciding to, well, I'm going to take some out of the account. I don't think returns are going to be that good this period, or I'm going to put all the money to work in the account in stocks, equities, if we're an equity account manager. And so if the manager is doing that and responsible for that, this would be the appropriate measure to evaluate that manager's performance. But it's just not usually the case. And so in general, what you want to keep in mind is that the time-weighted rate of return is the appropriate measure for evaluating the performance of an account manager. Now here we're solving for an internal rate of return. We're calling it the money-weighted rate of return, but you can see that it's very similar to what we did with the IRR. So we're going to solve for this IRR, but the reason these have to be equal periods is the IRR is an interest rate per period. So now if we've got quarterly cash flows in and out, our solution will be for a quarterly IRR. And so we really would have to use the shortest period between significant cash flows and use that throughout. So the periods must be equal length, and we use the shortest period between significant cash flows. But I think more what you want to get out of this right now is just an understanding, more of an intuition and qualitative understanding of what this money-weighted return is. So let's compare the two now. Here's the situation. We invest $1,000 at time 0. At the end of year 1, the value grows to $1,200. And we have a cash flow in. We add $800. And now at the end of year 2, the account value is $2,200. So we're going to use these figures and calculate both the annual time-weighted return and the annual money-weighted rate of return. Now here, our period for significant cash flows is 1 year to simplify this problem. Okay, so time-weighted rate of return. We've got 1,200 over 1,000. That's 1 plus our holding period return. Our first period holding period return was 20% here. The 1,000 grew to 1,200, so we had a 20% holding period return over that first year. Now, in the second year, it grows to 2,200, and we divide that by the 1,200 plus the 800 we added to the account. So at year 2, we've started out at 2,000, and it grew to 2,200. Well, that's a 10% return over this second year. And our time-weighted return it's an average. It's a sort of average of these, a little more complex than a simple average, but it's certainly going to be between those two numbers. And it comes out to be 14.89%. Notice we took this to the 1/2 power, this whole thing, because we had a 2-year holding period return. Actually, in the parentheses, or the brackets, and within the brackets, we've got 1 plus the 2-year effective return, so we take that to the 1/2 power minus 1 to get the equivalent compound annual return of 14.89. Now, what about the money-weighted rate of return? Well, remember, we're going to use those cash flows and solve this as an IRR type problem. So our first cash flow, we say we pay it into the account, so we'll say out of our pocket into the account, that's minus 1,000. Then what happens at the end of 1 year? Well, we added 800 to the account, so another 800 out of our pocket, or the corporation's pocket, and into the investment account. Now we've got our last cash flow. That's the ending account value of 2,200, and we're assuming we could take that out. Okay, so that's why we're giving that a positive value. And we solve for the internal rate of return of 13.623%. Notice that the money-weighted rate of return is lower. And it's important for you to understand why that is here. Our return the second period was 10%. Our return the first period was 20%. But we've got more money. We've got more weight, right? Money weighted. We've got more weight and more money on that second period. So the average we're calculating now is going to put less weight on the 20% return in period 1, more weight because we added money on the 10%. So that's why it comes out lower than the time-weighted return, which doesn't account for the different amounts of money in the account at the beginnings of the different periods. So if we use that IRR, just to show you that it is an IRR, if we discounted those two future cash flows at 13.623%, then the present value of those two cash flows is just equal to that initial minus 1,000. Okay, a few more things for us to describe here. We've got something called the bank discount yield, which always confuses candidates because it's not really a yield, and that makes it troublesome. What it is, it's a percentage discount from face value. Some securities are sold without explicit interest payments. We may buy a security at $980 and it'll pay us $1,000 at maturity. So this best bank discount yield is the discount over face value, but we make it an annual number by multiplying times 360 over the number of days to maturity. So that's just by convention. I know there's 365 days in a year. I realize we have a leap year every 4 years. However, I think this measure came up when things were a little harder to calculate back in the day before these little gizmos were available. So that bank discount yield is an annualized yield, simple annualization based on a 360-day year. Holding period yield, boy, we know that one already. I hope you've got that one down. Ending value over beginning value minus 1. Now, our effective annual yield, well, remember, we could annualize that holding period yield, and now we've got to use an exponent because we're talking about effective. We're looking at compounding within this. So that exponent there is 365 over the number of days. So we're taking 1 plus the holding period yield. So if it were about a quarter of a year, say 90 days is about a quarter of 365, then that exponent is about 4, a little higher than 4, because there's just more than 4 90-day periods in 365. So that's our effective annual yield. That's what you'd really earn over a 1-year period if you earned this holding period yield on a compound basis. And lastly, our money market yield. Money market instruments are instruments that mature in a year or less. Many of our discount type instruments are money market instruments. So here we're doing kind of a mixture of the two. We're going to annualize the holding period yield, so it's a true yield, and we're going to annualize it by multiplying times 360 over the number of days to maturity. So these are just 4 things you have to learn, and you're also asked in the learning outcome statements to be able to bounce around between and among them. Okay. And my suggestion, they offer some formulas in there, but memorizing formulas is always kind of a risky business. Whether you remember them at 3:30 in the afternoon, most of the way through a 6-hour test that's nerve-wracking anyway, your brain's getting tired, it's probably not the best way to do it. What I would suggest is you just key everything off the holding period yield. Be able to go from one back to the holding period yield, and then use the holding period yield, say, in another measure like this. So if you're given the effective annual yield and you're asked for the money market yield, I would just back that holding period yield out of there and then multiply that holding period yield times 360 over days to maturity. So let's take a look at some numerical examples. Make sure you have these down. Our example here is a 90-day Treasury bill priced at $9.80. This bill will pay $1,000 at maturity. That's the face value. So first we start with the bank discount yield. The discount on this T-bill is 2%, $20 over $1,000. But that's just for 90 days. We have to annualize it with our simple annualization, 360 over 90. So 4 times that gives us 8%. So that's our bank discount yield, an annualized discount. The holding period yield, straightforward. $1,000 at maturity, $9.80, the initial cost, ending over beginning minus 1, 2.04%. That's our 90-day holding period yield. Well, we can annualize that. We've got our exponent here, 365 over 90, so a little more than 4 90-day periods in a true 365-day year, minus 1. That gives us our effective rate there, effective annual rate or effective annual yield, same thing, of 8.53%. And you can see that's the highest of the numbers that we're going to calculate here. And lastly, a money market yield. Well, we just take that holding period yield, which we calculated as 2.04%, and use that simple annualization that we use for money market securities, 360 over 90 days, and get 8.16. And that's our money market yield. Now, let's define the bond equivalent yield. Why do we even have a bond equivalent yield? Well, bonds typically, at least in the U.S., especially in the U.S., pay semi-annual interest. And so when we say, yeah, I bought a 6% bond, if that's expressed as a bond equivalent yield, it really means that you earn 3% compounded every 6 months. That's when the payments are made. That's when the compounding period is. So that's why we define this bond equivalent yield as simply 2 times the semi-annual yield. So our effective semi-annual yield is, well, here we're going backwards, right? We're given not the stated rate, but you're given the annual effective rate. So the question becomes, what semi-annual rate compounded twice a year gives you an effective annual rate of 8%? So we're just going to take what we know and work backwards here. So instead of 1.04 squared minus 1 going forward with a 4% semi-annual compound rate, we're going to take that effective rate to the 1/2 minus 1 and find out that if we earn 3.923%, compounding was twice a year, our effective annual yield, remember where we started out with this stuff, our effective annual yield is going to be 8%. Now, let's go the other way in the second example here. If the monthly effective yield is 0.75%, 0.75, calculate the bond equivalent yield. Now remember, the bond equivalent yield is 2 times the semi-annual effective rate. We know the monthly effective rate or yield, so we can compound that monthly rate for 6 months. Our effective semi-annual yield, we take 1 plus the monthly rate to the 6th power, compound it for 6 months, subtract 1, and find out our effective 6-month rate is 4.585%. And what's our last step here? Again, that's a 6-month effective yield, double it, and there we have a bond equivalent yield. It's a way to put various securities on the same yield basis so we can compare them and see which one has the higher or highest yield. So let's just go through an example of these yield measures. Make sure you've got that down well. Certainly something that's very testable on the CFA exam. A 90-day T-bill is purchased for $997.40. Again, our face value we're assuming is $1,000. What are the discount yield, the holding period yield, the money market yield, and the effective yield? Well, you can tell. If you haven't kind of memorized what those are, you'd be in pretty much trouble right now. So what is our discount yield? Well, it's a 90-day T-bill. We're going to do the simple annualization with a 360-day year here. Okay? So that's why I put a 4 here. Remember, this is 360 over 90. And we get a discount yield of 1.04%. Well, what's our 90-day holding period yield? Again, that's the one you know for sure, ending over beginning minus 1. That is 0.2607, a little over 0.25% is your 90-day holding period yield. What about our money market yield? Well, remember that keys off the holding period yield, but we use simple annualization. We're going to multiply it times 360 over 90, same as we did to get our annualized bank discount yield, and see that the money market yield is 1.0428. That's going to be higher than the discount yield because the discount yield's not a yield. It's a discount. The discount yield is how much below its maturity value. The money market yield is how much extra do I make on what I invested. And then our fourth measure here, the effective annual yield. Remember, that's the real one where we use an exponent to get a true effective yield. Ending value over beginning value, and then we take that to the power 365 over the number of days until the security matures. That's 90 days here, and so that's our highest measure. We get 1.0614% as our effective annual yield. Okay, so that brings us to the end of this reading. I hope you found it valuable, and I'll see you again in the video instruction. Happy studying.